These are the acceleration problem exercises, and these are just the answers or the solutions to each one of them. For the first one, you do have your jumbo jet, and just a few things that we can tell about this jumbo jet. The first thing is its original speed is 45 meters per second. Its final speed is 0 because it does come to a stop, and it says that it takes about 5 seconds for it to slow down to that stop. At this point, we need to try to figure out what is the acceleration of the plane. So we can use our just basic equation, VF is equal to AT plus VO. We went ahead and rearranged it for this problem, and we're going to go ahead and plug all of our numbers in, and we should end up with -9 meters per second squared. For the second problem, this is number 2, you've got a car and the lady's driving her car 20 meters per second down a 4-lane highway. She does that, that's her original speed, and she decides that she's going to pass another truck, and she accelerates at 5 meters per second squared until she gets to a speed of 30 meters per second. They just want to know how long is it going to take her to get to that speed. We'll use our equation again. Acceleration is equal to the change in velocity divided by the time that has elapsed for that to happen. And with this one, what we did is went ahead and just rearranged our equation. The easiest way to rearrange an equation like this is just assume this is a over 1, and we're going to just switch what we have on the top and the bottom here on this side. When you do that, this is just a shortcut. We end up with t here and a here. The 1 stays on the bottom, and the VF minus the VO also stays where it is. Exactly the same thing. At this point, we can go ahead and plug our numbers in to the second equation. So we have 30 meters per second minus 20 meters per second divided by our acceleration of 5 meters per second squared, and we should end up with 2 seconds. For number 3, this is about Vivian the hairdresser. She's trying to get there. She's only traveling about 1.3 meters per second. She looks and thinks, oh no, she's going to be late. And so she accelerates at about 0.09 meters per second squared. Remember, she's walking. And they want to know what is her speed after 10 seconds. So notice in this problem, we don't have displacement. We don't want it. So the equation we want to use again is acceleration is equal to the change of velocity over the change in time. We can rearrange that to what we're more used to. The final velocity is equal to the original plus acceleration times time. Go ahead and plug everything in. Original speed was 1.3, acceleration is 0.09, and the time was 10 seconds. Go ahead and multiply the two together and then add the two numbers, and you should end up with 2.2 meters per second. And for this problem, that is approximately a jog is what you would see. For number 4, this one's about a billy goat. So we have Billy the goat, get it? Billy the goat, there's Billy the goat. And he is on a mountain. There's a rock that comes hurtling past him about 40 from a ledge about 40 meters above him. Billy ducks to avoid injury. They want to know how fast is that rock traveling when it passes Billy. So the important thing in this one is don't get confused by there's only one number given to you. We know that the original speed of that rock above him should be 0 meters per second. So let's say that this is a cliff and then there's a ledge above him that kind of looks like this, and the rock is just kind of hanging. Right before it falls, its original speed here is 0 meters per second. And remember, it picks up speed as it falls, so we'll talk about that next. We know that the equation we need to use is VF squared is equal to VO squared plus 2GD. You'll notice that there is no time in this, and we don't need the time, so we will use our third kinematics equation. And also notice that we're using G for acceleration. Anytime anything falls, we're going to use G, which is the acceleration due to gravity, and that value is approximately 10 meters per second squared. At this point, we can go ahead and start plugging some things in, or we can rearrange the equation. Totally up to you how you want to do it. In this one, we rearranged the equation, and all we did was just took the square root of both sides. So if I take the square root of both sides, we end up with the square root of VO squared plus 2 times gravity times the displacement, and that's equal to the final velocity. So we've plugged everything in. We're going to go ahead and do our math, and we end up with, oops, here's our final answer of 28.3 meters per second. Not sure why that happened, but it should be 28.3 meters per second would be the speed of that rock as it goes by his head. For number 5, this is about Reverend Northwick. Reverend Northwick was standing up in the steeple of his chapel, or the church belfry, and where the bells are held. He knows that when he drops a rock, it takes about 2 seconds for that book to actually fall. So it is a book, not a rock, but it takes 2 seconds to fall. From that, we want to know how high that belfry is. And this actually works if you use a very heavy object that doesn't have a lot of air resistance. The equation we're going to use is the one that has distance, original velocity, time, and gravity in it. So we don't have final velocity, and we don't need that final velocity. It does travel, and when it hits the ground, it does have a final velocity, but we don't need to worry about this in this problem. The next thing we need to do is go ahead and plug our numbers in. Our original velocity at the top is 0. Remember, anytime you drop anything, the instant you let go, it has 0 velocity, and it is accelerating. So this term goes to 0. We can plug in the 1/2, the 10 for our gravity, and then 2 seconds squared for our time. Go ahead and reduce down, and we find out that that church belfry is about 20 meters high. If you would drop this with just a piece of paper, that paper would float and you would not be able to accurately tell how high it is. Next problem is one that gives a few people trouble. You just have to be very careful. It says, how long is Tina the ballerina in the air when she jumps up with a speed of 1 meters per second? Notice that when she's at the top, she stops momentarily. And so her final speed at the top is 0 meters per second. We're going to make the up direction. So with this one, we're going to make the up direction negative. We'll make the down direction positive, and I'll show you why here in just a second. But for this one, we know that the final velocity at the top is 0 meters per second. Because of that, we're going to rearrange our equation, and we're going to plug everything in. Our final velocity is 0. We need to subtract off our original velocity. We made it negative, and the reason we made it negative is because it's pointing up. Gravity, we're saying, is going to be positive, and gravity is pulling towards 0, so we say that it is down. Now we can go ahead and solve our problem. We've got negative times negative would be a positive 1.8 divided by 10 equals 0.18 seconds. But be very careful, because this 0.18 seconds is actually just the time to go up. So just 1/2 of what's going on here. She also falls back down. So we need to go ahead and multiply our time up. So we're going to put up here by 2. If you multiply your time by 2, you end up with the total time for her to go all the way up and then come back down. For number 7, this is the next problem. We'll go ahead and switch the slide here. For number 7, you have a clam inside of a seagull's mouth. That clam will be dropped by that seagull several times until it hits the ground and finally breaks open. That way the seagull can get to it. Notice we have one number again in this problem, which is 25 meters. And we need to assume that going up and down, okay, our speed up and down, or our speed in the y, is equal to 0. Even though the seagull might be flying in the x direction at, let's say, 5 meters per second, it is not moving up and down. So our y speed is 0. That clam, he will drop then, or she will drop it. And we want to know how long does it take for that clam to fall. Notice that we have an original velocity. We don't really have a final velocity, and we don't need that final velocity. And so because of that, the kinematics equation that we need to use is the one with distance, original velocity, time, gravity, and does not include the final velocity. Gravity again here, we're on Earth, so it's 10 meters per second squared. Go ahead and plug everything to our equation. Multiply both sides by 2 first in order to get rid of the half. Once we've done that, we're going to divide both sides by 10 to get the 10 on the other side. And then finally, we need to take the square root of both sides to end up with a time of 2.2 seconds. So at that distance of 25 meters up, that seagull, when it drops the clam, takes about 2.2 seconds to fall. This is exercise number 8. And for exercise number 8, That we're at an amusement park. You've seen this ride before. I know that they call it Drop Zone at Kings Island. And it basically just takes you up and then drops you. It has a height of 33.5 meters, and that's the only number they give us. So at this point, we know that the original velocity is 0. They don't give that to you. You have to remember that anything that falls drops with an original speed of 0. And gravity is about 10 meters per second squared. The reason we're using this equation is because we don't want to know uh, at what time it takes it to fall, and we've not been given a time. This question just wants to know how fast is it going at the instant that it starts to slow down at the very bottom. So not when it actually hits the ground, but when it would just start to slow down before it would hit the bottom. So our final speed squared is equal to 0, which is our original speed being as we're dropping people. That we add to that 2 times gravity, which is 10, and then 33.5 meters. We're assuming that this is going down, and so we're using positive numbers. We can go ahead now and multiply 3.5 by 10, multiply that by 2, we get 670. And now notice that we need to take the square root of both sides. If you take the square root of both sides, you end up with 25.9 meters per second, and that would be how fast they're traveling at the fastest point down at the bottom before they start to slow down so that they don't get hurt. The last problem here is number 9, and for number 9, we're going to go through and just take a look at it. A unique type of basketball is played on planet Zarth. It tells you that a player basically jumps really high, flies above the basket, and then drops it from a height of about 10 meters, which is pretty high. If the ball takes 5 seconds to fall, find the acceleration due to gravity on Zarth. So we've been given a distance of 10 meters. We know that the original speed of the ball is 0 meters per second. We know it takes that ball 5 seconds to fall. Notice that we do not have the final velocity of the ball, and we don't need the final velocity of the ball. So at this point, we're going to find G. We are on another planet. We're not on Earth, so we cannot use 10 for G. Instead, we're going to use an unknown, and we're going to say we're going to find that unknown number. We'll use our equation. Since we don't have final velocity, we don't need it. We're going to use our kinematics equation with distance is equal to VOT plus 1 FGT squared. Go ahead and plug all your numbers in. 10 meters is our displacement or our distance. VO is 0. We're going to have 1/2 of whatever gravity is on that planet times 5 seconds squared. Go ahead and I'm going to multiply both sides by 2. Once we do that, we can divide both sides by 25, and we end up with the value for acceleration due to gravity on planet Zarth of 0.8 meters per second squared.